Hey guys, so next I'm going to be doing a Newton's law of cooling equation, and I'm going to show you both how to set one up and how to solve one. So first we need to make sure we write this right here. So what this is this equation here is saying that the change in temperature, that's just one numerator there, that's not a negative sign. I can't write always perfectly. Anyway, so we're dealing with the change in temperature by some change in time is equal to some constant k times the difference between the temperature of the object and the ambient temperature in the room. So from here, what we're able to do is just bring this over. So we're then dealing with a minus t, dt on top. So we've just brought this over here by dividing the right-hand side. And then we're going to multiply the left-hand side by dt to bring dt over. So then we're dealing with dtk. And from there, what we're going to be doing is we're going to be taking the integral of both sides. So we'll pop an integral sign on there, and there. So on the left-hand side, we have negative ln of a minus t. And that negative just comes from the fact that when you take, it's chain rule, so you take the derivative of ln of some u, which is 1 by that u, and then you take the derivative of that u function. In that case, our derivative is just negative 1. So that's why that negative comes out from there. If you're still not sure on that, I can message me privately and I can help clarify for you. So then we have that's equal to kt. And as usual, we're going to be adding a c on top of that. So to make things a little neater, let's take out the negative sign on the left-hand side and pop it in on the right. Again, because we're dealing with an arbitrary constant, that sign can still be positive. So to simplify this and get it all in terms of t, we're going to take put both sides to the power of e. So that means over here we have a minus t is equal to some c1 e to the negative k t. And that's actually equal to e to the negative k t plus c. But because, again, c is an arbitrary constant, we can just simplify e to the c as c1. So that's why I've done that there, and that will make your life a little easier. So we've got the sort of beginnings of an equation here. The next step we're going to do is keep on rearranging. So from here, long story short, you're going to get t is equal to a plus c1 e to the negative k t. So that's your final equation there. If you put a over on the right-hand side here, you got c1 minus a, and then you could just flip the negative on both sides. And again, because c1 is an arbitrary constant, the sign on it doesn't actually matter. So we're going to solve for our initial conditions. In the description, I put a link to the question so that you can take a look and have that open while you're following along. So first thing we're going to do is we're going to solve our initial condition. So t at 0 is equal to 90 degrees. And we also know that our ambient temperature is equal to 25 degrees. So if you'll bear with me for a moment, I'm just going to slide this up so you can see a little better. So we know that 90 is equal to 25 plus c1 e to the 0 is equal to 25 plus c1. So we know that c1, oops, that's a g, c1 is equal to 65. So now that we know our c1, we can solve for our k value. So from there, we're just going to plug back in. So t is equal to 25 plus 65 e negative k t. So now what we're going to do is we know that T of 1, so 1 minute after we've started to let it cool, is equal to 85 degrees Celsius. The units don't actually matter as long as you're consistent with which ones you're using. Obviously Fahrenheit and Celsius are on the same scale, so it doesn't matter. It can even be Kelvin. So, so we know that 85 is equal to 25 plus 65 e to the negative k. Just a 1 there. So from that, you're able to solve that k using your calculator. You're able to solve that k is equal to negative 0.08. So the way we do that is just rearrange so that on the left hand side you have 60 by 65 is equal to e to the negative k. So you can just take ln of 60 by 65 to solve for k. So now that we have our k value, we're able to solve for when the coffee, or what is it? Coffee, yes, coffee is cold enough to drink. So we've got, let's rewrite our original equation. So we have T is equal to 25 plus 65 e to the negative 0.08, excuse me, T. So we also know that we're trying to find T at some x is equal to 30 degrees. So, same as before, we're going to just plug that in. So 30 is equal to 25 plus 65 e to the negative 0.08 x. And I'm not going to show you how to solve that out, but at this point you are dealing with an x of 32 minutes, which is what the answer was. So that's how you solve a Newton's law of cooling question. This initial part, let me just grab a different color so I can highlight it. This part right here is critical for you to know, because this is actually, I think, a fair amount of marks on the tests and whatnot. So you'll be able to get a couple marks just by putting this, the derivation. And if you don't put it and just jump straight to this, you'll lose marks. I'm going to make, even though it wasn't on the test, I'm going to make another video on exponential growth and decay, just so you guys can get an idea of that as well. Thank you very much. I'll see you on the next video.